Hello students. Today we're going to begin a new unit called Kinematics. What kinematics is it's the study of motion. What we're going to do is we're going to take what you learned from the physics skills and apply it to the mathematics within the study of motion. All right, so let's begin. To start with, you need to be able at the end of this to explain what the different types of speeds would be, whether we're looking at just generic speed, distance over time. Are we looking at average speed? Are we looking at constant speed, instantaneous speed? So what's the difference between those? Are we looking at velocity? Is it a positive velocity, a negative velocity? All right. Will you be able to properly identify if something's in motion relative to a frame of reference? So what exactly is a frame of reference? And then lastly, probably my favorite thing is to look at the mathematics that's involved with this area of physics. All right, now there are a couple other terms that we're going to throw in here. If you look at the bottom, it says displacement, position, and vector and scalar and magnitude. Well, before we start in on the details of speed and velocity, what I want to do is show you a real short video clip on what vectors and scalars are, because we're going to use those terms throughout the whole lesson. So if you don't get a real crisp picture of what they are, you're going to struggle just a little bit. But I don't think anybody's going to have difficulties after watching the video. So let's get that going.
Assume you're standing at this point. Now, if your friend tells you there is a treasure pot 50 kilometers away from home, how long will you take to find it? Which direction will you go? It could be here, or maybe here. It is hard to know where exactly it is. You are only provided the distance, which is one-dimensional information. One-dimensional information like this is called a scalar quantity. Your question to him would be, which direction from home? When you are told that it's 50 kilometers in the northeast direction, you have the precise information of the location. This now becomes two-dimensional information, distance and direction. The treasure pot is over here. Two-dimensional information like this is called a vector quantity. Scalar quantities are one-dimensional and vector quantities are two-dimensional. Speed is a very good example of what we call in physics a scalar quantity, indicating only magnitude but not specifying any direction. So that's what scalar quantities are, only magnitude but no direction. In the case of velocity, however, the direction is stated, and that's why it is referred to as the vector quantity. A vector quantity involves not just the magnitude but also the direction. When you add directional information to speed, it becomes a vector quantity called velocity. The additional information makes it more specific. Temperature change, for example, is one-dimensional quantity. But when we specify rising or falling temperature, it is two-dimensional. If someone says that the temperature has changed by 2 degrees, we won't really know if it has increased or decreased.
All right, from the video, what you should have gotten is the term scalar refers to some measured quantity without direction. So here, there is no direction associated with scalar quantities. Scalar quantities, it could be distance, it could be time, it could be mass. These things are measurements that have no bearing on direction whatsoever. Okay? Now, on the flip side of that, and before I go on, I'm going to put in here speed because that's the big topic for today. Then when we look at what are vector quantities, you have something with a magnitude, all right, a number, a measurement, but this one has direction associated with it. All right, so the similarity between vectors and scalars is they both have some sort of magnitude, some sort of number associated with them, but the difference comes in play when vectors, all of a sudden, you're describing a object's velocity, an object's acceleration, the force that's imparted on an object. So those are measurements that are going to have not just a quantity, but a direction associated with them also. Now, if we were to draw these out, scalar quantities, this would be, let's say, a representation of a distance. You notice that there's no arrow indicating whether this distance moved was to the right or to the left. And the length of that scalar quantity will help to describe what the magnitude is. So this one right here, it's smaller, so this would be maybe 5 feet instead that would move. All right, so roughly half of that. A vector quantity, on the other hand, vector quantities here, this would be an example of 10 feet to the east or 10 feet to the right. And then again, if we're looking at the magnitude, how big these are, if I draw the vector quantity smaller, that would represent a smaller magnitude, and the direction is still to the east. Now, an easy way to remember what scalars and vectors are is to refer back to Despicable Me. Despicable Me, the movie.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
The villain in it, his name was Vector. And when he introduced himself to Gru, he said he was committing crime with both magnitude and direction. That was a physics term within the movie that they fed to you. All right, we're going to take a look at motion first, because you can't describe how fast something is moving unless you're able to identify that it's actually in motion in the first place. And in order to identify if something's actually in motion in the first place, you have to establish what is referred to as a frame of reference. A frame of reference is going to be some object that typically is not moving around. And that's kind of difficult to do because everything pretty much in the universe is moving around. You might say, well, no, a building's not moving. Well, technically it is, because the Earth is rotating on its axis. It's rotating around orbiting around the sun. The sun and the planets in the Milky Way galaxy are moving. So when we are trying to describe this, we'll try to narrow our scope down to just thinking about, in relationship to other objects on the Earth, what are things that don't typically move. So in our classroom, we might describe the desks. The desks are bolted into the ground or into the floor of the building, and buildings don't typically move, okay? They don't sprout legs and start walking down the street. So if we use the desks in our room as a frame of reference, so right here we use a desk, and if we compare the position of a person at different times, if that person changes position relative to the desks, then we know without any doubt that that person was in motion, and we can calculate what that person's speed would be while they were moving. All right, so in physics, the word position simply refers to the location of an object at any one instant. So if we know where the point of origin is, where that position was at first, and then we know where the person ended up at, we can calculate two different things. We can calculate the distance that that person has moved, and we can calculate the displacement that that person has actually moved. Now we can, from that distance or displacement and the time, also determine, from putting those items together, we can figure out what the speed or velocity is as well. But before we get into speed and velocity, let's look at what the difference would be between distance and displacement. All right, now that is going to be done in the form of a little brain teaser here. So let's say that you're going to go hunting. This is your cabin. And you are going to hunt for bear. So when you leave your cabin door, here's your cabin door. Now, if you walk due south 1 mile, okay, you see no bears. So you turn and you walk due east 1 mile. You see a bear and you shoot, but you're a poor shot and you miss. That angers the bear, and the bear chases you due north 1 mile to where you close your cabin door and you're safe. The question I have first is, what was the color of the bear? Right? You might be thinking, what in the world? But let's come back to this. All right. Let's figure out first what the difference between distance and displacement was. How far did this person walk? All right, so total distance. So the total distance that this person walked would be pretty simple. You have 1 mile, 2 miles, 3 miles. So this person will have walked a distance of 3 miles. Now notice, I just said that they walked a total of 3 miles. See, distance is a scalar quantity, and we don't put a direction on it. It's just a total, grand total distance, 3 miles. All right. Now, if we look at the displacement, that's a little different. Okay. Now, before we answer what the displacement is, and before I get to the color of the bear, hopefully you're still thinking about that, let's look at another thing that you might be questioning. You might be saying, wait a minute, Pullman, if I go due south 1 mile, so this is south 1 mile, and I go due east 1 mile, and I go due north 1 mile, I can't be back at the same point. Well, technically you can be, because there is one place on the earth that you can actually do that. One place on the earth that you can actually do that is at the North Pole. You can go due south 1 mile, due east 1 mile, and then due north 1 mile and be back at the exact same spot. So this answers the question, what color was the bear? The bear is a polar bear, so they're white. Okay? Now, let's get to that displacement thing. Displacement is a vector quantity. Vector quantities have both magnitude and direction. So, if our person was at the North Pole and they started at the cabin, they walked south, east, and north, and they ended up right back at the exact same spot, displacement is how far away were they from when they started? Well, if they started at the front door and they ended at the front door, their displacement, how far away were they from their starting spot, was 0. They were 0 miles away from their originating position. All right, now in Upper Sandusky, if we were to look at that example, if you go due south, east, and north 1 mile respectively, now in Upper Sandusky, if we started here and we ended here, what is the change of position from when we started to when we finished? Well, this would be a displacement of 1 mile to the east. See, distance, we don't have any direction associated with it. Displacement is a vector quantity. We have both magnitude, quantity, right? And we have a direction, east. Vector, quantity, magnitude, direction. All right. Now, these magnitudes and directions, what we use is a coordinate system to help keep things organized. Now, coordinate systems can have positive and negative values associated with them. So, the easiest way to do this is to just look at a normal piece of graph paper and we put an X and Y axis on it. Now, yes, the Z axis would come out of the board at you, but for this purpose, we're just going to look at the X and Y axis. So, a vector quantity, let's say that somebody's going to walk to the northeast. Typically, you say that this is going to be the north and that's the east. All right. So if we describe the direction now, this person, the X and Y value, what would the values be for it? Well, in terms of positives and negatives, the X axis, when we go to the right, that's going to be considered a positive value. And then as you go up on the Y axis, that's going to be positive also. Let's look at another vector. Let's say that we have a longer walk that you take from our point of origin. We're going to go to the southeast now. To the southeast, here, our X value, we do go to the right, so that's positive. And we go downwards, so that would be negative. So we have our coordinate values there. Let's take a trip. We're going to go northwest this time from our point of origin. Shorter distance, shorter magnitude. And our X value here is going to be negative. The Y value, it goes up, so it's positive. Last trip that we're going to walk. If we have a really long walk that we're going to take, okay, our vector or graphical representation is going to be longer. And this time, since the X value, it's going to the left, it would be negative. And the Y value, it's going downward, so it would be negative also. So keep in mind these positive and negative values on our coordinate system because it will help you out immensely when you're trying to describe things. All right. A real simple explanation of where we would apply these positive and negatives is if you have a car and it's going to take a trip and it's going to go 100 miles due east. Now, due east means it's not going to go up or down, north or south, all right? So it's just straight to the east. All right, that car stops, and then what's the car going to do? It's going to turn around, and it's going to drive backwards 50 miles towards the west. So the question is, how far did the car travel? That's a scalar quantity. It doesn't care about direction. So the car's total distance here would be 150 miles. But what is the displacement? The displacement, how far away are we from our originating point? Our originating point is right here. The distance away from our original point would have to be 50 miles to the east. So 50 miles to the east is where we ended up at. All right. Now, these vector quantities, as you can see, we are going to use them in three-dimensional space, but we're going to keep it easy at first and only look at one-dimensional problems, just as I did with the car. Okay, the 100 miles, back 50 miles, that would just be a simple one-dimensional problem. So before we move on, let's make sure that we have that term really memorized. A vector quantity is going to contain both magnitude and direction. And we can describe that with the coordinate system of those X and Y values. All right. So if we have that idea of what scalar quantities are and what vector quantities are, let's dive a little deeper into what one of our scalar quantities would be. Speed. So if this guy right here is a scalar quantity, we know that we have some sort of magnitude associated with it. No direction, just a value. And we determine what that value is by figuring out the rate at which distance changes. You know if your position changes, you're in motion. So your distance is changing. Well, how much time does it take for you to change? See, in physics, the word rate means the ratio of how much something changes divided by how long it takes. So we're going to look at a formula in a moment, but before we do, let's take and imagine that you're in your car. you're in your car. The first type of speed that I prefer to travel at is a constant speed. One of the biggest pet peeves that I have when I'm driving somewhere is the person that either has their foot on the gas or foot on the brake and there's no consistency. It drives me insane. So if you are in your car, what would you need to do to get a constant speed? Well, the easiest thing would be to turn on the cruise control. If you turn on the cruise control, you're going to maintain a fairly constant speed. You're going to have a very similar speed for every single second that you're driving. All right. So what would be an example of this would be our bicycler right here. Our bicycler, for every single 1 second that passes, they travel 1 extra meter. So they'd be traveling for every single second 1 meter further distance. And then the bicycler in the bottom, they have a faster speed. All that means is that for every single second that passes, they travel 3 meters instead of the one before. Okay. Now we looked at what constant speed was. Constant speed, we have the same distance traveled for every single second, but there are other types of speeds. Okay. And there are other types of units that we can use for this. See, the bicycler, they were traveling at meters per second. But would you use meters per second when you're on the highway? No, not really. You'd use miles per hour, or maybe if you were in Canada, kilometers per hour. And likewise, if you were traveling on the space shuttle and you're blasting off into outer space, you wouldn't use feet per second. So that ratio of distance over time, you have to make sure that you're using the appropriate units. All right. So our constant speed, I'd like to go on a trip would be the speed limit and put the cruise control on so that way it's not going up or down, speeding up or slowing down. Okay. We know what speed is. It's that change in distance per unit of time. We know what constant speed is. That's our cruise control. Now, let's say that you can't put on the cruise control. You're driving through town and you're hitting every single red light and you're having to speed up and slow down. How are you supposed to figure out your speed there? Well, that's called our average speed. And there's 2 ways that we're going to calculate the average speed. That's where we look at the total distance traveled and then divide it by however much time it took you to get there. Before we get to those 2 formulas, we'll look at our last type of speed, and that's the one where you're going to look at your speedometer in your car. You look at the speedometer in your car, that's going to tell you your apparent speed at that one moment in time. And if we're graphing out a position time graph, the slope of the line is actually going to tell you what your instantaneous speed is. Okay, we'll come back to that. So our formula, if you're trying to calculate the average speed, we can denote that we're looking at average speed by just putting this little line right above the V. That tells us that we're looking at the average. So if average speed is looking at the total distance, we put a little triangle in front of it. Now that triangle, what exactly does the triangle represent? It represents the Greek symbol delta. Delta means change in. So if you see a triangle in front of one of our variables, it just means that it's a change in. So we have our average speed. You look at the change in distance divided by the change in time. It's a whole lot simpler putting in the delta symbol than writing in change in for each time. All right, so that's one way that we can calculate our average speed. Our second way of figuring out our average speed would be similar to that as you working with your test grade averages. If you wanted to figure out what your average on 2 tests would be, you add them up and you divide by 2. So 80 and 90 You add them up, divide by 2, your test average would be 85. We can use that same process and look at two different speeds and use those two different speeds, add them up, divide by 2, and it's going to be your average. So we're going to put that formula down here as well. I really want you to start on a formula sheet. You've got your first one up on the board right now. And the second one, if you're looking at average speed, we take the two speeds, you have 1 and you have 2, and you add them up, and then you divide by 2. But the problem here is that you see V plus V. Well, we need to decide which one is the original speed by putting an O down at the bottom, so that way we know what speed we started with. And then we put an F for the final speed. All right. So these two equations, this one and this one here, you need to get on a formula sheet. I'll let you use your formula sheet on every single homework assignment, every single quiz, every single test, on the exam. I don't care. If you put the effort into writing down the formulas, you get to use them. If you don't, well, you better have a good memory. Okay? Now, we looked at those. Let's actually put this to work now. We're going to use the guess method that you learned back in the physics skills. So I'm going to write down guess. I'm not even going to read the question. What I'm going to do is pick out the variables. I see 450 kilometers, and I see 10 hours. Those are the only two numbers I have. I'm going to label these. Kilometers is distance. Hours is time. That's it. That's the only numbers I have. So what's the unknown? It says, what is the average speed? So average speed in, you ready? Meter per second. So you're going to have to use two skills. One, we're using the guess method, and then two, you're going to have to factor label. You're going to have to do a little bit of dimensional analysis to change kilometers to meters and hours to seconds. It's not difficult to do. Our formula now, you have two to pick from. So the first one you have is this right here, right there. Well, I know the distance, I know the time, and I'm trying to find the velocity. So that looks like the equation I'm going to use. I don't want to use this one because I don't have two different velocities. All right. So we'll plug this in. Our equation, we have distance over time. Now we're ready to substitute our variables in. We have 450 kilometers. We have 10 hours. And what we need to do now is we need to factor label this. We need to change the units. So 1 kilometer is the equivalent of 1,000 meters. And 1 hour is the equivalent of 3,600 seconds. All right, so we're going to put those two conversion factors in here using that bookshelf method we learned before. All right, I'm going to cross-cancel kilometers. I want to get rid of it. So I find that in my conversion factors, and I put that in the bottom to cross-cancel it. That means the remainder of my conversion factor goes in the top. The last part, we need to get rid of the hours. So I see hours right here. That means that portion of the conversion factor is going to be cross-canceled up top. The rest of that goes in the bottom like that. We're ready to answer this thing. We know that velocity, average velocity then, you would have to plug this in. I don't have the number memorized. If you got 450 times 1,000 divided by 10 divided by 3,600, you come up with 12.5 meters per second. All right. On your math problems, that's exactly what you have to do. You have to show your work like that. I'll give you the answers. You have to show me the process of how we get that. This is a fun one. Just get away from the math for a second. Let's say that you have two bicyclers. Both of them are traveling at a speed. Well, we should say velocity, really, because velocity, we know that this guy is moving to the left at 10 kilometers per hour, and that this one is moving to the right at 10 kilometers per hour. They are 20 kilometers apart. So if both of them are traveling 10 kilometers per hour and they're 20 kilometers apart, they're going to come together in 1 hour, aren't they? And the question says, how many kilometers did the bee travel if it's bouncing back and forth from tire to tire to tire to tire? How far will it travel before it gets squished by the two tires? Well, if the two bicyclers are going to collide together in 1 hour, and the bee is traveling at 30 kilometers per hour, that means that the bee can travel 30 kilometers. Before we jump into graphing this, let's do a quick review. With a typical graph, if we just have two data points, we've got 0 and 10 and 10, okay, as our ordered pairs. If we were to figure out what the slope of this line would be, you would take the rise, how far up does this go, and that is 10. And then how far over is the run for that is 10. You divide them and you get 1. So the slope of our line is going to be the ratio of rise over run. Let's label the x and y axis now. If we label the y-axis with distance and the x-axis with time, how does that change things? Well, now the rise for this, we know the value for the rise was 10. If we put the unit on here of centimeters, and then the run of this was 10, and if we put the label for the unit on there, that was seconds. Now what do we end up with? We end up with a speed. We don't just end up with a slope, we end up with a speed. Notice I didn't say velocity because there's no direction here. So we know what the speed is. Now, since this thing right here is a straight line, this is what we would consider to be a constant speed. All right? Straight lines are constant speed on a distance time graph. If you have a distance time graph where it's a horizontal line like this, that means that it's a constant speed. Constant speed is 0. You're not moving anywhere. But it's a constant speed. The values that we would have on one of those graphs, if we start describing the values in terms of positives and negatives, you're no longer looking at speed. On one of those graphs, when we start describing the motion, the speed of our object in terms of positive and negatives, you are now looking at the velocity of that object, not the speed of the object. So, two examples of this. You have the cars in the picture here. So this car, it's moving to the left. So left would be on our coordinate system to the back side of our point of origin to the left. So that would be a negative value. The green car is moving to the right. So that would be considered a positive value. A good example of this would be if these two cars were moving, we have one is to the right and it's traveling at, let's say, 100 kilometers per hour, but it encounters a headwind. Okay, that's the velocity that the car is able to do, but it encounters a headwind, and the headwind is producing, let's say, a 20 kilometer per hour headwind. What will the velocity of the car be then? If it's capable of doing 100 kilometers per hour, but it's got a headwind that's resisting that, then our resultant is going to be 80 kilometers per hour to the right or to the east. Okay? One-dimensional problem. So we see here from these one-dimensional problems that velocities have both positive and negative values. Let's apply that. Here, when the direction of motion is part of the calculation, changes in the position are referred to as displacement. Remember, displacement, how far are you from your originating position? So let's break this little diagram down right here. First off, we have a constant speed right here, all right? And we know that this object, this car, has traveled 60 kilometers. They've traveled 60 kilometers, so I'm going to write down 60 so I know. It's traveled 60 kilometers during that time frame of 1 hour. Then what happens right here? Well, right here during this segment, we started at 60 and we end at 60. So right here, they stop. There is no motion. It might be described as a constant speed of 0. We go to the next part. Here, the car is now again traveling at a constant speed, and it gets to 90 miles away from its starting point. Okay, so we have 90 miles from this starting point here to there. Now let's draw a linear picture of this. That's like right here, this is 60 miles, and then they travel another 30 miles. So this grand total is like them traveling 90 miles. When we get to that spot, all of a sudden they take another stop. How do I know that's a stop? Because the position doesn't change. We're now on the way home. So on the way home, they're coming back to their starting position. Remember, its starting position was right here. This is like the house, like that. So the house is right here in a linear picture. The car went 90 kilometers, and then they came back 90 kilometers. So I have two questions. One, what's the total distance that this car will have traveled? Well, it went 90 this way and then 90 back. So that means that the car has traveled 180 miles in total. But what is the displacement of the car? The displacement of the car, they started at the garage, they ended at the garage, so the displacement would be 0 miles. They are at the same starting point. Let's take a look at the next thing. The next thing would be calculating our average velocities from that same graph. See, average velocities are going to use those values of the displacements from 0 to 60, from 60 to 90, and then from 90 to 0. Those are displacements. If we use those values and then the elapsed times from each of the positions on that graph, what we can do is we can use a formula. Yay! Another formula write down. We can use those values and our formula to figure out our average velocity. So let's look at one of these average velocity problems. An average velocity problem, we're looking at the change in displacement divided by our change in time. All right, so let's look at what our displacement was. We started right here, right? The car went a total of 90 miles, and then it came back 90 miles. So what's our displacement from beginning to end? From beginning to end, for our distance final minus distance original, it was 0. If we divide it by our time frame of 4.5 hours, it really wouldn't even matter because anything 0 divided by anything is going to be 0. So our average velocity there would be simply 0. Now, if you wanted to, let's say instead of going from the starting point, if you were going to, let's say from this point here to this point here, if you were wanting to figure out what the average velocity was during just this segment, So if we say that that is our starting point right here, we would have to take and say that our change in distance, our displacement, we ended with a 0, right? Right here is where we were at. We go and put miles, minus the 90 miles. That's the number up here, 90. We divide that by your time frame. What was that? 1.5, 1.5 hours. So what we end up with here is a negative value, don't we? See, when we work out the math, we end up with a negative value. Is that okay? Sure, because remember, on the coordinate system, if it's going downwards like this, that's going to be a negative value. All right? We're going to look at this graph one more time, and this time we're going to be looking at the instantaneous velocity during each segment. So, for the instantaneous velocity, we look at any point along this straight line right here for part A. I know that during part A, I take my 2 points here and here. My rise was 60. My run was 1 hour. So my instantaneous velocity, what was the speed on my speedometer as I was driving along? It was 60 miles per hour. So we have an idea of what these different slopes can help to tell us. They can help to tell us what the velocities are. Those velocities, our formula is basically going to be the same thing as what speed was. Speed, since it was a scalar quantity, it was just distance divided by time, and there was no direction with it. But when we're looking at velocity, velocity is going to be distance over time, and there is going to be some sort of direction associated with it. So if we take that change in distance and divide it by our change in time, that's what we've got. Now that change in distance over the change in time, delta D could be, and same thing with delta T, it could be written out as the distance, the final distance minus the original distance divided by our end of our time on our stopwatch from our beginning time on our stopwatch. Okay. We have 2 more graphs that we'll take a peek at. The next one is where we're going to change the y-axis just a little bit. See right here, our y-axis before was labeled as distance. Our x-axis remains the same. That's time. All right, we're going to see how this differs just a little bit and sometimes why it can be confusing for people. So, from this graph, what I can see is that I have a straight line coming across right here, and that's going to be my velocity. My velocity is to the right at a velocity of 1 meter per second. So, why is this one considered to be moving when this one right here is considered to be not moving? See, this line is coming straight across right like that. So why is this one 0? Because it's describing position. The position right here does not change. This is 60, that's 60, so it did not change position. When we look at the new graph, we're not looking at distance, are we? Here, we're only looking at the velocity. So this particular graph, if we changed it and we put time here and now we put distance right here, what would we see? We would see something that would look like this. This slope on a distance time graph, that, excuse me, that would represent 1 meter per second. See, when we change the y-axis, we are going to change the look of the lines like this. Okay? The neat thing about velocity time graphs is that the area that's underneath the line actually tells you how far you drove or how far you went. See, if we count up these boxes, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means that I have gone 10 meters. Mathematically, how does that work out? Well, if we look at that formula for velocity, I know it's distance over time. If I rearrange this and I go time like this to cancel it, if I want to figure out the distance, I'd multiply the velocity times the time. Our velocity was 1 meter per second. The time was 10 seconds. Our distance then would be 10 meters. Okay, it's just something neat to see. We will work on a couple of these when we do graphing. All right, but that finishes us for this particular lesson. The items that you should have gotten from this. First, motion is a change of position relative to a reference point. 2, speed and velocity, they're different. Speed is a scalar quantity. Velocity is a vector quantity. Horizontal lines on a position time graph show no motion, but if you have horizontal lines on a velocity time graph, that shows you constant speed. On that position time graph, the steeper the slope that you have, the faster you're moving. The shallower the slope is, the slower it's going. What you have to do is make sure that you have filled in all of the blanks. Not everything in these notes will be completed just yet, because we'll cover the rest of it in another day. After you have finished up all of your blanks, you're going to submit this to Schoology. Okay? And then we have part B to this assignment that you'll need to work on tonight. All right? If you have questions, ask. If not, go ahead and get your work done, and we'll move on to the next thing tomorrow.